Hello, this is Martha Rivera from the Academic Support Center. Once again, this is Calculus 1. We're looking at techniques to analyze limits. Now, the first thing that we're going to look at are the limit laws, and these are taken from pages 72 and 74 in the book. And the example looks like direct substitution, but it helps us know how to break things up. So let's go over the laws a little bit. So with the limit laws, if we have two functions that are added together, let's say x squared plus x cubed, we can take the limit of each function separately. It would be like the limit as x approaches of x squared plus the limit as x approaches x cubed. We can do the same thing for a difference, where we can take each function and apply the limit to each part and then subtract them. So if we had something where the limit as x went to a of f of x was 4, and the limit as x went to a of g of x was 3, we can compute the limit as 4 minus 3. Now, anytime we have a constant, so if we have something over here in plus 9, that's a constant, and the limit of the constant is always the constant. So as we break up a function into its component parts, if we're left over with a constant, that stays the same. It just stays what it is. Now, we can also take functions that are multiplied together and take the limit of each of those. Same with division. We can apply that limit to the numerator and the denominator. If we have something raised to an exponent or a fractional exponent, we can do that as well. So if we take an inner function, let's say we take the limit as x goes to a of whatever function, right? And it comes out to be 2. And it was squared. So we know that we can take 2 and square it, and that the limit would be 4. So I just pulled this example from the textbook because it's a little bit quicker to go through. So we have an algebraic function up here. Doesn't this look like fun? Awesome. So we can do direct substitution, no problem, to solve for it. This example illustrates how we can break that up to take the limit of each component part. Because sometimes if we could do like half of the work by finding the limits and then do like algebraic manipulation on the rest, it's another way to look at it, and it can make our life a little easier. So let's take a look at this. We've got this fun function, numerator, denominator. We apply the limit to the numerator and the denominator. That's our quotient law. And then we can, within the numerator, we have two separate functions up here. This under the radical, and then we've got 3x minus 1. So we separate those out and take the limit of each of those. And in the numerator, we just have one function, but we can take the limit. Now that everything's broken up, we can use direct substitution to put 2 because we wanted the limit as it goes to 2. And this is one where you can use direct substitution, but these limit laws are helpful to know what we can do, how we can manipulate or change a formula appropriately while keeping its integrity, and make our life a little easier or learn a little more. All right, the next way, so we covered the limit laws. The next thing that we can do is factor. And factoring is awesome. So what we do is we take the numerator and the denominator and we factor them out. So up top, we want the limit as x goes to 2. If we put 2 in here, we have a problem, right? We'll end up with 2 squared or 4 minus 4, and that does not work. We can't do that because we would get 0 in the denominator, and it would be undefined. So let's see what we can do. In our numerator, we have x squared minus 6x plus 8. Can that factor out? What multiplies to positive 8 but adds up to negative 6? Well, 8 times 1, 2 times 4. Oh, there we go. So we've got x minus 2 and x minus 4. Because if we take and we multiply negative 2 and negative 2, we get that positive 8. and if we add them together, that gets us -6. So we've got some work done in the numerator. Now let's look at the denominator. The denominator is a special form called a difference of squares. Anytime we have a squared minus b squared, and that's anything squared minus anything else squared, where there's a perfect square, that equals a plus b times the quantity a minus b. And so we've got x squared, which is a perfect square, and 4, which is a perfect square. So we can use this property, this law, as a perfect squares to split this into x plus 2, x minus 2. If we step back and look at our equation here, we can do some canceling because all things up top are multiplied together, all things below are multiplied together. This x minus 2 is essentially 1. And we're left with x minus 4 divided by x plus 2. Now that, we've just done a little we've done factoring or algebraic manipulation, and we've kind of unmasked a little bit, and we want the limit as x goes to 2. And now we have x minus 4 over x plus 2. Because when we factored each, and then when we cancel out or unmask the 1, up here, this is what's left over. Now we can do direct substitution, no problem. So we put 2 in for our x. We've got 2 minus 4 over 2 plus 2. 2 minus 4 is -2. 2 plus 2 is 4. And we can reduce this a little bit. Take a 2 from each. And we've got -1 over 2. And this is how we can, it's a way to analyze limits by using factoring, those good old fundamental techniques from algebra. And knowing the perfect squares helps. Another technique we have to analyze limits is to use conjugates. Now, what are conjugates? Conjugates are when you have a pair with a plus, minus. So if we think back a little bit to imaginary numbers like I, it's always going to be plus and minus I. And so conjugates are when we have the plus and the minus aspect. Now when we have radicals in limits, the party radicals, oftentimes using conjugates and multiplying by the conjugate pair can simplify our life. So we're going to rewrite this as, here we've got this radical x minus 1. So the conjugate pair is going to be radical x plus 1 over radical x plus 1, because we're really just multiplying the function by 1, and that's allowed. So let's rewrite it down here. We've got the limit as x goes to 1 of square root x minus 1 over x minus 1. And if we used direct substitution, we would have 0 in the denominator, which would be undefined. And so this is why we're using the conjugate pair. And then multiplied by square root x plus 1 over square root x plus 1. Now a tip that I have is whenever you've got these two down either in the numerator or the denominator, this conjugate pair that you're multiplying by, don't factor it out. Don't FOIL it out, I mean. And see if, wait till the last step, because sometimes keeping it in this form can help. So let's do FOILing up top. We do square root times square root. Square root x times square root x is just x. Then we've got square root x times positive 1. That gives us plus square root x. Then we've got minus 1 times a root x, and that leaves us with minus root x. And then we've got -1 times positive 1, which results in -1. and we're going to keep the denominator unfoiled. So x minus 1 times square root x plus 1. Now let's simplify up top a little bit. We have a plus radical and a minus radical. That means that they cancel each other out. So if we rewrite, we've got x minus 1 over x minus 1 times square root x plus 1. And now we can cancel this out because the terms in the bottom are being multiplied together. This x minus 1 is a common factor for both. So now we've taken this limit that we couldn't evaluate before using a conjugate. We're left with the limit as x goes to 1 of 1 over square root x plus 1. And this we can do direct substitution to evaluate. So let's do that. We've got 1 over square root of 1 plus 1. Square root of 1 is just 1, so we've got 1 over 1 plus 1, or 1 over 2. And when evaluating the limit with a radical, sometimes try using a conjugate pair to see if that can help simplify and make it so that you can evaluate that limit. Well, this is it for this video. Let us know if you want more examples or anything that we could do more in depth. Have a great day.